You are welcome. In today's video, I'm going to talk about transform of derivatives, finding the Laplace transform of the first derivative. This function is dx dt. When we transform dx dt into Laplace, we have f bar of t, or sometimes I just say f1 of t. Now, if this is new to you, locate the video Introduction to Laplace Transform Part 2, Transform of Derivatives. I have already discussed how to transform a derivative function into a Laplace transform. It will help you to get the concept. So now let's box on. Before I begin, kindly take some few seconds to support this work. Subscribe to this channel if you haven't. Click on the notification button for more updates. If you don't need updates, you don't need to click. You just have to subscribe. Alright, so the Laplace transform or the Laplace transform, whatever way you want to call it, L of f bar of t is the same as the first derivative. We learned that in the beginning, from Intro to Laplace Transform Part 1, we learned that the Laplace transform of any function is given by the integral from 0 to infinity. The function given times e to the power negative st dt. If you look at Intro to Laplace Transform Part 1, I discussed the t is already the first derivative of the variable t, and t is a real number beginning from 0 to infinity, or it must be greater or equal to 0. S is the complex part. Let me not talk much about this. You can locate that video. So now this is what we have. Now we have two functions, f bar of t and e minus st multiplying. Now anytime you have an integral of two product functions, what comes into mind? Integration by parts. There are exceptions depending on the kind of function you are working on. Sometimes you can avoid integration by parts, but for this one, it is necessary I apply it. Now, what is integration by parts saying? The formula says that the integral of two separate functions multiplying is integral of u dv must be equal to u v minus the integral of v du. Now this is what integration by part is saying. It said treat one of the function as a variable u and then treat the other function as a variable v that has already been differentiated. Now this is dv. That means the derivative of the second variable. Now this means that multiply the two variables, which is equal to the product of the two functions minus the integral of the second function times the derivative of the first function. Do we get that? Now because I have 0 to infinity here, I can put my upper and lower limit here. It's not necessary, but we can put it there. Now, be very careful which of the functions you have to choose to represent u and which of them should represent dv. For this function, it is very easy to choose. For other functions that are not in this form, you can just pick the first one as u and the second one as dv. But watch carefully. This function is first derivative, f bar of t. So I would have to pick it to represent dv. Then I'll use minus st to represent u. This is because multiplication is commutative. It is very important I do that. So now we say that let u be equal to e to the power minus st, and let dv be equal to f1 of t. This is because this is already a derivative function, so it qualifies this one. Straightforward. It doesn't mean this is how you go about it every time. You can just choose the first function to be this, the second function to be that. Now, what is our next step? Your next step is you need to differentiate the function u equal to this to generate du dt, because we do not have du function, so we need that. So let's do it here. Once we differentiate du dt, what are we getting? The differential of this is equal to negative s e to the power minus st. When you have a function e to the power at, the differential of this is equal to, use this to multiply, a e raised to the power at. So whatever coefficient you have here, we'll just multiply the function. This is how you differentiate an exponential function. When you look at this, the coefficients there is negative s. So negative s e to the power the same minus st. Now, let's come to the next one. The next one, all you need to do is to integrate the function to get v, because we already have the v. If I differentiate the v, I'm differentiating the second time, which will give me the square v over the t square. I don't want the second derivative of this. I want the main function. So to get the main function, we need to integrate what? The v. Now the integral of the v is going to give us what? V. And the integral of f bar of t is going to give us what? F of t. I guess you got that concept. So if I have the variable v, then the derivative of v will give me dv with respect to something. Let's say dv dt. Then if I have dv dt, when I integrate this, I'm going to get what? V. So the reverse process is what we have here. Now we have v to be equal to f of t, and we have du dt to be equal to minus s e to the power negative st. All you need to do, pick this result and substitute it into this formula. Now, what is the formula saying? It says uv. Where is u? We have u to be equal to this, so we put in u. So we have e minus st times, then we have v. What is v? V is the same as f of t. So multiplying f of t. Okay, then we put this in one bracket. The formula said minus. Now remember, you must introduce your lower and upper limit. So this is it, minus the integral from 0 to infinity, multiplying v. What is v? V is the same as the function f of t times du dt. What is du dt? This is du dt, which is the same as this one. We have times minus s e to the power negative st. You can add the dt, there is no need. So now, but let me do that, times dt. Don't forget we even have dt here. Okay, so times dt. Now we can break this down again by using this negative to multiply this and bringing the s outside. So we have e minus st times f of t. We raise our lower and upper limit. Now negative s times this will give us plus s integral of 0 to infinity f of t times e minus st dt. Once we integrate the function, dt will vanish. Now when you get here, you need to take the limit. I want to avoid that, so we are going to input our upper and lower limit into the function. Remember that I said in the beginning that t here is representing real values that is between 0 to infinity. So here, this is equal to t, this is equal to t. Do we get the concept? So wherever we see t, we have to input infinity and 0. Do we get it? Now inputting the upper and lower limit, the result is supposed to be upper limit minus lower limit. So let's do that and see the result. So now this becomes e to minus s into infinity times f of t, t representing the upper limit, you close bracket, minus, we input our lower limit, the same result, e to minus s of 0 times f into 0, then plus, we continue the remaining function, s integral 0 to infinity f of t e minus st dt. Remember, we are working on this side. This is where we introduce our upper and lower limits. So I input the upper limit into the function. This is it, minus the lower limit. Now, from what we have done so far in this playlist, when we take the limit of a function e to the power minus t, as t approaches infinity, the result is equal to 0. I've been saying this. It means that as t approaches a very large number, the result converges to 0. You can punch this on your calculator. Substitute t for a very huge number. For instance, 1 billion, 2 billion, okay, 1111555. Just do that. The result will be what? 0. So we know that everything that we have here converges to what? 0. Everything we have here converges to 0. So as t approaches infinity, the result here is 0. So all this side becomes 0. But watch very carefully. This side, anytime you raise to the power 0, for instance, t to the power 0 is equal to 1. E to the power 0 is equal to 1. Okay, so this side we are getting negative 1 times f of 0. Remember, this is not 0. So now the result here becomes 0 minus 1 times f of 0 plus s integral of 0 to infinity f of t e to the power negative st dt. Again, we do not need this 0, so we can get rid of it. Now, f of 0 here is a transform of derivative when t is equal to 0. For the sake of explanation, I will take you back to transform of derivatives, and with that, we will be able to understand the concept. In transform of derivatives, let x be equal to the function f of t. When t is equal to 0, the result becomes x naught, which is the same as f of 0. So transforming this result or this function into Laplace transform, we can say that as t is equal to 0, then the function x is the same as x naught, and we replace 0 here. So f of t is the same as f of 0, which is the same as x naught or x subscript 0. So now we know that f of 0 here is very important because it is representing t equal to 0. So you don't say it is 0. So from here, we can now use f of 0 to multiply negative 1. Forget about this 0. So when you multiply this, this is minus f of 0 plus s integral 0 to infinity f of t e minus st dt. Now we are done with the calculation, but we need to start applying knowledge. As we get here, we need to remove this one and replace it. But what are you supposed to replace this with? Watch very carefully. It's very simple. All we need to do is that the Laplace transform of the function f of t is the same as integral from 0 to infinity f of t times e minus st dt. We all know this one. Now this is the same thing we were applying here. Watch carefully. The Laplace transform from f bar of t was equal to this. So if it is the main function, it will be equal to the same thing. Now watch. Everything that we have here is equal to this. Okay, so now I can replace all this side except s with what? This one, to cut the lengthy equation short. So from that explanation, you just quote that, but the Laplace transform of f of t is this. So we can do that substitution. So the equation becomes minus f of 0 plus s multiplying this one, L into f of t. And this can be your final answer. So the Laplace transform of f bar of t, which is this, the result is equal to this. Now, you can leave the answer here, or you can change everything into a notation. If you watch transform of derivative, we can transform everything here into notations. So let's do that. Earlier on, I said that if x is equal to f of t, then when t is equal to 0, then x becomes x0, which is equal to f of 0. This is what will help us to change this result into notation. Now, the first derivative of x, let me say the t, is the same as x dot. The second derivative of x, which is this t square, or in terms of y, you can use y, is the same as x dot dot. Again, the Laplace transform of the variable x is equal to x bar. Put that in mind. Watch the video transform of derivative. The Laplace transform of x is equal to x bar. So with this knowledge, we can say that the Laplace transform of x is x bar. Then what will be the Laplace transform of the first derivative? The Laplace transform of this is equal to s times x bar minus x0, where this x0 is coming from here. This s bar is coming from the Laplace transform of what? X. Okay, so watch that video, transform of derivatives, introduction to Laplace transform part 2. It will help you to get this concept. So now we can just do the substitution. F of t is the same as what? X. So the Laplace transform of f of t is the same as x bar. Now do you get it? Now f of 0 is the same as what? X naught. So we pick this one, then we multiply by s. So this is the same as minus x naught plus s. The Laplace transform of f of t is what? From the paper, x bar. So this will give me what? X bar. So finally, you can write your final answer as the Laplace transform of f bar of t will give you the result s x bar minus x naught. I just decided to write the s first. You see this one? So this is your final result. You can also leave your answer here, but I prefer working it to this end. So this is your final result. So all you need to know is to know transform of derivatives. So thank you for joining me. This is the end of this one. I will see you in the next video.